Okay, let's see, we need some camera. All right. Well, let's. Hello, hello. Let me browse. Let me look for the YouTube channel. How are you all doing? I hope you're all doing great. Let's see. Let's see if I'm good enough to find my YouTube here. Where is it? Oh wow. Not even that. Maybe I need to put myself on the other side. That'll do it. Oh, here it is. YouTube. In the meantime, I can fix my hair while I get the information. Let's go into quantum mechanics for students. Okay, so this is a nice little video that I found in the internet.
Delta T, you're in H bar 2, which will come.
Find it very interesting because the guy is trying to.
That's what the word means. And it deals with the smallest.
Explain quantum mechanics. Watch this. Watch this guy. I mean, I admire him.
So, how many of you guys know what quantum mechanics or have taken a quantum mechanics course?
Okay, so he's figuring out how many people know it.
Okay, cool. So we're gonna go.
Now, noticing that expression, you know, he doesn't know. He realizes that a lot of people in the class have never had quantum mechanics, so he's about to start fresh. And the title of this video is Quantum Mechanics for High School Students. So this is gonna get interesting.
Over the basics of quantum mechanics. So what quantum means is just discrete.
All right, good.
That's what the word means. And it deals with the smallest units of matter.
Okay. Now, he's having trouble explaining what quantums are. Yeah, they are discrete values that you find, and by definition they are, you cannot break them apart. But as you can see, it's kind of hard to explain what a quantum really is. So let's see what he does in order to try to conceptualize it, in order to make it clear for the students.
Objects in the universe, subatomic particles, deals with things at a very small distance. And weird things happen at this distance, such as particles could behave like waves and wave behaves like particles. They become pretty much indistinguishable.
So he's talking about a very small scale kind of events, and usually that is the case, but of course, if you have been following the news, recently there was a report of macro system, a big system that actually behaves quantum mechanically, and it's a big system, but generally speaking, yeah, it refers to something very small, but not necessarily. That's where you usually find it. I think it would have been better for him to give an example, the atom or something, right?
So, like some of the effects of this is, let's just say this eraser is a quantum particle. If I throw it at a wall, sometimes it will get reflected, but sometimes it will go through. It will pass right through the wall.
All right. So now he's jumping around into different concepts. Okay, so it's moving and then it's bouncing back and forth. I know exactly what he's trying to get. He's having a hard time to set up, something tangible for the students.
That's just, it goes against our basic understanding of how walls work. And more non-intuitive, I feel like this is more bizarre. If this is a quantum-sized object, and we roll it off a table, every time just a macroscopic eraser will go off the table, but sometimes it'll get reflected back.
Okay.
Now the best way to understand this weirdness of what happens with quantum mechanics is to do an experiment. So I'm going to go over the double slit experiment. So
So he went into jumping in a wall. Now he's going into a different thing. He's going into double slit experiment, which has nothing really to do with the bouncing that he was talking about. So he was trying to describe the effect of, I guess, kind of sort of hinting towards tunneling, right? But now he's going into the typical double slit experiment, which shows that these quantums, these pieces of things, behave also like waves. So jumping around to something
We
else
have
completely.
a detector and we have a screen with 2 slits in it.
Okay.
So if you throw classical balls, what happens is at the end, so the detector at the end will measure the ball being here, will measure the ball being here.
Okay.
Now let's look at classical waves. If we have a single slit, what happens to the waves? The wave will come in and hit the detector pretty much at 1.2, the most intense point. It'll have like some like fuzziness around the edges of this point, but that's just because of the it's decreasing in intensity. If you put 2
Okay, so he's going into one slit, I guess.
slits, and you put 2
he's trying the
classical
double
waves
slit.
going in, what we get is called an interference pattern,
Right.
where you get bright spots on certain.
So of course, I mean, I'll just jump around. I'll skip this part. So he's talking about when waves go through a double slit. Sometimes the waves add up in some points. Sometimes they cancel out in other points. So you get what is called an interference pattern. And it will be good to give an example here. I gave an example one time in a bar to a guy putting 2 bottles of what would they, Coronas or whatever they were. I don't know, they were Heinekens, I think. And I tried to speak through the bottles, and I mentioned to him that if the waves that I produce were about this, had the wavelength more or less of the distance between the 2 bottles, you would start getting an interference pattern, which means if you go on the other side, you would hear in some places clearly the sound. In the other ones, the volume goes down, so it would go up and down as you move around the bottles. Okay, so all right, just to make it a little more tangible for anybody.
Areas of the screen and dark spots on the other. Okay. And that's just when the 2 waves meet up, when their wavelengths or amplitudes add up. So for example, let's just say one wave represents.
Let's go a little further.
More bizarre is if we shoot 1 particle at a time through this. So it could either go through this one or this one. What happens is we still get the same interference pattern.
So now he's now talking about the crux, what is weird about quantum mechanics. So if you start shooting 1 quantum at a time, you want to expect to get a wave pattern on the other side, right? It looks like kind of like when you throw balls. I mean, you don't expect to see a wave pattern on the other side because you clearly see that they are balls or something, something contained in one little space, and you're throwing them with some trajectory. So that's the analogy that he's making, and of course, it's typical that one typical weird thing about quantum mechanics is that you actually get interference pattern on the other side as if it were a wave. Okay, so this is not bad in the way he's explaining it, and I just want to say this, and I will keep saying this over and over again. It's very hard to explain quantum mechanics to beginners, and he's doing his best, and it's kind of hard, but he's getting to a place where it becomes a little more concrete. I would just say he needs to add a few more examples here.
On the opposite
concrete
edge.
Examples.
So, but this doesn't make any sense because there's 1 particle going through the slits. There's nothing for the particle to interfere with. So we say that the particle, so let's say this is slit 1, slit 2, it goes through both slit 1 and 2 at the same time. and interacts with each other. And if you put a detector on one of them, then it goes back to behaving classically. So
one thing I like about what he's doing is how he points at things. He turns around, and he's doing a he has great diction, and he is using his whole body to explain things and pointing to things, and that's very important when you are teaching a class.
when you know which one it goes through, it becomes a classical, it acts classically. But if you don't know which one it goes through, it's quantum mechanics.
Right. So, okay. So, yeah, that's good. Let's see what else he has to offer. Let me put it forward a little more. Okay. So, this is a part that I find
in quantum mechanics, because just like the act of measuring changes the state. So we say the difference between these measurements is I H bar, and I is just.
So he jumped from. I mean, these are beginners. He's talking about what is called quantum states and operators, and of course, I mean, this is okay, but I think he hasn't spent as much time explaining what a state is and what the operators do, and not every high school student, I'm pretty sure, is acquainted with non-commutative algebra. So it's interesting how he jumped from one thing into the other. He's giving a very formal description of that. So at this point, it would be interesting to see what the students say.
Square root of -1. So
I have a question.
Yeah.
So you were talking about the order of the measurements.
Yes.
So then the first term means you measure the position first, and then the momentum secondary.
Yes. Unless I might have screwed this up. Did I reverse the order?
No, that's
Okay. Yeah.
Okay.
So
I know there computational relation that
Yeah.
one. Yeah, but I just know that it's come from like so the characteristic from matrices or the.
Yeah, so notice how this guy seems like he understands what's going on here, so he's trying to clarify. And notice he mentioned the word reversible. What he's trying to get is it's a very interesting point. Basically, in quantum mechanics, when you measure the momentum of something, and then you measure the position, you don't get the same thing if you measure the position first and the momentum later. Okay, so that's what it means by non-reversible. So measuring one thing and then measuring the other is not the same as measuring. If you reverse that, you don't get the same result, and that's pretty much what, in more simple terms, that's pretty much what he's getting at. And I think he's trying to ask a question, and he's really very attentive, trying to see what he's gonna ask. So let's pay attention to where this goes. I think it's gonna go into an interesting place.
Operator.
Yeah.
But so if you're talking about the order of the measurements, so then I don't get what you mean.
So here we can define just x as x, and we can define p as h bar over I d by dx. Okay.
Okay. Yeah.
So now let's just say we have a function, we have a state. So we have x p. We act on a state, so we have x p minus p x.
All right. Well, I'm not sure if he understood the question, but he's computing some more. Let's see where these gets.
So now we get x h bar over I d by dx f minus d. And now, see this is where it comes in, so careful here. So h I. So now I x on the position and I x on the function as well.
I see. So what he's doing is now he's trying to. So, so instead of explaining, the concept, he went into getting what is called now the representation of those operators, doing more math around here. And again, it's very hard to explain something like this abstract to beginners. I recommend to anybody watching this video to read the Feynman lectures on physics, the third book. I think it does a great job in trying to explain quantum mechanics without all the calculus, and he builds up the math, very smoothly. It's hard though. It's hard to try to understand it, but it sort of helps for those of you who want to have an introduction. Let's see how far you go. There's the whole book. Basically, it was based on real lectures, and it turns out that a lot of students didn't do too well. So it's a failed experiment. So I know that's why I'm interested in watching this video. This lecture for high school students, because it's a hard thing to do, and I think it's worth attempting to do it, because quantum mechanics is. It's sort of I think it's a sort of neglected subject in high school, and I think there's room to actually do better. Okay, so let's continue here.
So now if we calculate it, run through a quick calculation, we use the product rule, or the product rule. So this is just f(x).
So I think I'll move these forward because I think he's just he's still on the same concept, trying to demonstrate it. Let's see what happens later. So he keeps doing more math, I can see from the board.
Quantum field theory, for example, when we have a field with no particles in it, and we start making these operations, it would it would be a completely different state.
Okay.
It'll mess up the state. So
okay. It's interesting how he's jumping into quantum field theory. Okay, he hasn't covered anything about substantial on quantum mechanics. He's jumping into quantum field theory, and he's trying, I guess, to do his best now to explain something about quantum field theory. Again, kudos for his desire to try to teach these to high school students.
We'll see that later on in the course.
Oh, we'll see that later.
For now, yeah. Sorry if I just went off on a tangent, but yeah. So that's good for people who haven't.
He realizes he went on a tangent. Okay, but that was a very, very abstract tangent.
I've seen this before. So this is.
I hear something out there. Okay, never mind.
These commutation relations are very important. So it's what makes, if you have a classical theory and you impose these commutation relations on your theory, it's quantum mechanical. You make it quantum mechanical. So they're very fundamental to your.
Yeah, I guess what he's saying is that if you have that non-reversible operations when you do a measurement, well, then you are talking about quantum mechanics, right? Because if you, just think about it. We don't have to get too abstract on this part. If you measure the position of something and then you measure its velocity, you get the same thing if you measure the velocity and then you measure the position, right? But in quantum mechanics, you have the sort of the unusual situation where if you measure the position of something and then you try to measure the momentum, you get something different. If you try to measure first the momentum and then you try to measure later the position of the particle. Okay, weird. Okay, and that's connected to something called a Heisenberg eccentric principle, but and he just presented that. So if you're kind of lost, okay, well, it's there's more to that, but bravo for trying to. Let's see how far he goes into the subject.
Formulating the theory of quantum mechanics. So the next thing I want to talk about, for those who haven't taken quantum mechanics, is particle in a box. This is the first thing you're going to talk about when you study quantum mechanics. Right. So let's just say you have a.
So I can see he's trying to go into the typical problems very quickly. I can see he's settling down for something, more something more concrete. So typically, so basically, the particle in a box is basically what you get when you attach a rope on a wall and you start, bounce. You start shaking the rope. You start seeing these waves going like kind of like that, right, back and forth. Once you see the waves sort of looking like this, okay, am I doing it right? Ooh, there you go. Ooh, waves. Once you see waves going like this, back and forth, actually, it will look something like this. Okay, so first it looks like this, but then eventually you start bouncing it just right, and it just kind of looks up and down in every place. That's pretty much the equivalent of a particle in a box. Okay, so hey, there you go. So as I suggest to him, okay, just give a concrete example. You don't have to get so abstract, but let's see what he's gonna do for that, for the particle in a box.
A box or region of space. These boxes aren't real. It just represents a region. We'll start studying boxes. Asking where they came from, if they're fundamental or not. But for now, the box just represents a region of space. We say the length is A, and this is the endpoints. So a big thing about
what he's doing
this
right now. Let's see how far he gets into that.
modeling quantum particles. I think I spelled that right. Oscillator, yeah. Okay, so instead of dealing with a box, we just say, there's some potential. And we write the states.
So now he's basically changing the configuration. Instead of a box, what if we have a different way of reflecting the waves? Like what if the reflection goes more smoothly? Okay, that's what he's trying to draw. So I don't hear anybody responding anything. When you're teaching high school students, it's good to check once in a while to see how they're responding. And so far, and right here, I see him looking at the board all the time. I haven't heard any questions. I've been skipping around, but as you can see, mostly it's a one-sided conversation.
In this notation. So this is the ground state. We say it's the zero state instead of the first state.
Yeah, so the ground state is pretty much when you have a wave bouncing back and forth between two boundaries is pretty much one wiggle. Okay, because you're gonna have less than a wiggle, right? There's gonna be if the wave is bouncing back and forth between two boundaries. Okay, well there's one wiggle that you can form, right? Kind of like that, one wiggle. Like, see, if you have two wiggles, it kind of looks something like that. I cannot do it. 3, 4, so the lowest one is just one wiggle. That's it. Okay. All right. Let's see.
The second state, so on and so forth.
Right.
And the energy level is given by the state.
High school students.
It's just E H bar omega.
Well, give it names. Okay, let's see. What else? Cool. Right in.
That's so 0. So this is the 0. So this is n. So n is in here.
So that's for the harmonic oscillator.
So
okay, good. Why is he gonna quantize it like that? Yeah, because that's what you need.
We have this object, this cool object that adds 1. We have this cool object that lowers 1. So now let's look at these normalization factors. Let's just say we have state 3.
All right, so let's see how far he gets. He keeps going on the same idea.
Equal this. Something weird I want to point out right away is that the lowest state it could have. So right now, let's just say, taking gravity aside, I'm just standing still. Like, what would my energy be? Yeah, so 0. So it's weird now that once you get into the quantum mechanical level, in order for the particle to exist, because if it goes lower than zero, it doesn't exist.
Yeah, well, okay, so he's saying that the lowest possible energy is 1 wiggle, not zero, like, right? So if you're standing in one place, your energy is zero, but here the energy of 1 wiggle here is the lowest one, so it's not zero. But it's more clear, I think, for students if you actually do this, right? 1 wiggle, okay? Because it's not possible to be like this in quantum mechanics, right? Because as he was talking, you got waves, and when you have waves bouncing back and forth between two walls, well, 1 wiggle is the lowest possible energy, right? As simple as that.
In order for the particle to exist, it has the energy 1/2 h bar omega.
Okay.
That is just something very strange about quantum mechanics.
It's not strange, even waves either, okay?
And that is because the plates are in such a small region, so they're so close together that the laws of quantum mechanics. So you have to take quantum mechanics into account now. And one of the uncertainty principles is a change in energy is a change of time. So you can't be certain what your energy as time. So for
right, so now he's going back to the uncertainty principle, right? And by the way, I mean, he didn't go into it very clearly, but just by looking at the board, I imply that. Because, basically, you get sort of the equivalent of the uncertainty principle if you measure things with waves, right? If you have waves, okay, obviously, if you try to measure the momentum of a wave, it will be there will be some uncertainty between measuring the position of the wave and measuring the momentum of the wave, right? It's not like when you're measuring a particle, right? So you see a particle here, well, yeah, I can measure the velocity and the position at the same time, but if you have a wave like this, well, it's different, right? So it's there's nothing really weird about quantum mechanics in this part. It's just wave mechanics, okay? So I guess he could have explained something like that instead of saying it's weird. I know we people when people study quantum mechanics, they like to look at things in a really weird way, but certain things are not that weird, okay? Or they used to be weird for the people when they came up about with this stuff, but there's even more weird stuff in quantum mechanics that is worth mentioning. Not this one, but let's see how far he gets. He's doing a great job, okay, trying to go through all these things for high school students.
a small amount of time, energy just pops into this vacuum. So it perturbs the vacuum. So we have a vacuum with no particles, but because we're so close, because we're looking at a scale so close, what happens is energy just pops into existence. And they are taking the form of virtual particles. So we have virtual...
So now he's going to quantum field theory. Now let's see how much of the previous information he uses for quantum field theory. So he's talking about how the vacuum is really not a vacuum. You can have virtual particles being created and annihilated, okay? But it's a huge jump from quantum mechanics in a non-relativistic way, that's what this is. This is quantum mechanics at for speeds less than the speed of light, you could say that, and he's now jumping into some results that actually come from looking at particles in area at velocities comparable to the speed of light. Okay, and with those equations is how you come up with these results. So it's very interesting how he just jumped into the next big thing. But hey, kudos, he's keeping the attention of those students. Okay, I don't see anybody throwing anything, so that's great.
Particles popping in and out. of existence in this vacuum on the inside and the outside. And because of this boundary condition, the number of possible virtual particles could exist is higher.
I believe this is part 1. Do I have part 2? Let me see. Do I have part 2 of this video? Probably I do have part 2. Let's see if I can find it well. Yeah.
Nothing. Cool. So that's what.
Okay, a little forward.
So we have virtual particles popping in and out of existence in this vacuum on the inside and the outside.
It's about to be over.
And because of this boundary condition.
Okay, so it's about to be over. So, well, let's see if I can see the next part of this one. There's no part 2 here. Okay, well, too bad I don't have the part 2. Well, all right, well, I guess I can say I salute you for trying to teach quantum mechanics for high school students. And as anybody can see, the task is a lot harder, and but I think it can be done. I know it's going to get to the point, to the point where, you know, it's going to be required because so much is coming out in quantum mechanics, and there's so much that is being done, you know, more weird stuff than the stuff that he mentioned, like, believe it or not, teleportation, you know, which is a really bad name. You know, there's something called entanglement, and well, those are the weird things. But I think he tried, you know, he tried to do a wonderful job, and he maintained the attention of the students. So I salute you.